So the next talk will be given by Grigory Paderin from Research and Technical Center of Gazpromneft.
Good evening, everyone. I'll talk about theoretical study of self-similar fracture growth in a pseudo 3D formulation. As you know, hyaluronic fracturing is the creation of crack in the rock by high pressure injection of fluid with sand or proppant into the reservoir. Hyaluronic fracturing is the main method of efficient recovering hydrocarbonates in low permeable reservoir. First of all, let's talk about main assumptions of pseudo 3D model. Firstly, we assume that a crack develops in a vertical plane and the length is much greater than the height of the crack. So, the fluid flow along the crack is assumed to be quasi-one-dimensional and directed horizontally. And the crack growth in the high is determined by mechanics of Black-Scholes fracture. And fracture growth in horizontal direction is determined by fluid flow. We have several layers P, and the one of them is permeable with thickness H, and the leak-off from the permeable layer is described by Carter's law, where Te is the time when the leak-off starts from the crack element with the coordinate x. It means that the fracture leading edge at this time is present, it's initiated in this element. So this function could be inversed, and the inverse function describes the law of fracture growth. So let's talk about main equations of pseudo 3D models. The rock deformation is described by linear elasticity. The fracture growth in high is described by Irwin criterion when K1C is fracture toughness. The fluid flow in the crack is described by a continuity equation. It is the law of local volume balance. It is the main governing equation of this model. And fluid flow in the crack is described by lubrication flow. So these all equations could be reduced in these main governing equations, where Kf is the flow consistency index and N is the flow behavior index of power law fluid. In this study, we want to investigate self-similar solution. So I have main assumptions of desired solution is that the leading edge of the crack propagates uniformly straightforward with the constant speed. We take that the speed is equal 1 divided by alpha. This means that we are looking for the solution in the form when our pressure is dependent from one independent variable, and we name it tau, where tau is time minus the time of element time initiation. So using this assumption, our second order partial derivative equation could be reduced in second order ordinary differential equation. To solve the presented equations, we must set the boundary condition. First of all, we find the value of our independent variable at fracture tip, and it's equal to 0. Then we set the first boundary condition. It is the value of our pressure. It's presented on the slide, and then the so to define Cauchy problem, we need two conditions at coordinate tau equal to 0. So we used the no leakage condition at the crack edge. It means that the fracture velocity of crack edge is equal to the average velocity of fluid. So using these two conditions, the presented equation can be integrated one time analytically. So it's lead to the first order ordinary differential equation. This equation is quite simple to solve numerically, and I'll present the results. At all pictures, when the fracture contour is presented, the blue lines means the position of fracture contour at the time equals to 20 minutes, green line to 40 minutes, and red line to 60 minutes. In this picture, in this slide, the three pictures presented from left to right. It's the minimal leak-off coefficients, and at the right side we have the maximal leak-off coefficient. So we see when we at the same other parameters, the increase in a leak-off leads to an increase in crack height and the crack volume at the same propagation velocity in our solution. So let's check how the injection rate depends on the leak-off coefficient. As you see for these pictures, at the same propagation velocity, an increase in leakage will require a significant increase in flow rate injection. Let's study how injection rates depend on crack growth propagation velocity with the same leak-off coefficients. As you see, from these pictures, leak-off injection rate also increased by propagation velocity. And in this slide, the left, the dependence of injection rate on velocity presented at time equal to 0, and the right picture is equal to 60 minutes. And we see that when the fracture starts to grow, this dependence is linear, and when the fracture is rather big, this dependence is highly non-linear. So the main results of the work, the first, that the self-similar solution analysis with the assumption of the constant fracture propagation velocity was presented, And due to the formulation of the problem, instead of no linear partial differential equation of the second order, I get the no linear equation, which was ordinary equation, which positively reflects of complexity and calculation. And an increase in leakage rates leads to increase in crack volume at the same growth rate. And as you see from the pictures, an initial moment required injection rate flow is proportional to crack growth velocity, but over time, the crack propagation velocity required a sharp increase in injection of flow rate. Thank you for your attention. I will be glad to answer the questions.
Okay, thank you very much, Grigory, for perfect timing and interesting report. So we are now open for questions, please. Yes, Nikolai Nikolaevich, please, your question.
Thank you. Well, it was an interesting solution. As far as I understood, in your solution, just the self-similar solution needs some special history of injection. So the injection of fluid should be performed following some special strategy, being dependent on time. Is it so?
Yes. In classical problem of hydraulic fracturing, this schedule is set it, and usually we have constant injection rate. So the speed of fracture propagation, it is
it's not
constant.
Okay.
But in my study, I set the velocity of fracture growth to the constant, so I'll get
you need a growing injection rate.
Yeah.
You need growing. Okay, that's understandable. And the other question, what about the pressure in the tip of the growing fracture? Because it seemed to me that here you have some final value of the pressure in the tip, the fluid pressure in the tip of the fracture.
The fluid pressure at the tip is constant as the boundary condition, yes. And the fluid pressure at fracture bottom hole, the point when the liquid is injection, is rising during the pumping.
Is rising. Okay, I see. But how can it be? Because as far as I know, this here you use one-dimensional law of Darcy type for the fluid flow, just the some drag coefficients, and it was demonstrated in self-similar solutions obtained, I think, more than 20 years before by Jose Adachi, Emmanuel de Tournai, and Dmitry Garagash, that under this assumption, in the absence of fluid lag in the tip, the pressure should be minus infinity, just to guarantee fluid pumping in the channel, which thickness decreases to 0, and we need to deliver fluid there to the tip, where the thickness is exactly 0. And so for this, for Newtonian fluid, it is necessary to have infinite pressure drop. And that's why somehow I was a little bit surprised that here in your model, you do not have a fluid lag, but nevertheless, the final pressure in the tip. Please, some comments on this effect.
Yes, this is one of the problem of this pseudo 3D model. I just use model from literature, and I studied Adachi works. They have this line fracture tip, and they studied some fracture, the leg and the distance from this tip. So I just set this boundary condition when I'm sure the fracture is opened, and I don't study the question of fluid lag. These conditions, number one, means that if we know exactly fracture high and is H, and we our fracture in one layer, so we can define the fracture pressure, and it is not equal to 0 to
No, zero is possible because mostly it is equal to 0. Actually, in the fracture tip, in the fluid, where if one has a fluid lag, then it is equal to the partial pressure of vapor at that temperature, there, the pressure inside. But yes, it's bad when it is minus infinity. It cannot be. So as far as I understood, you used the boundary conditions people usually make for the case of fluid lag. But since you are constructing a self-similar solution, which doesn't permit having any lag, because any lag, it's another linear dimension, and then self-similar solution doesn't exist. And so you solve this problem by just making the length of the leg 0, but nevertheless you assume that in generally it exists, and pressure in the tip of fluid is just similar to the pressure at the boundary of the fluid and fluid leg, and not in the, so you assume some final thickness in the tip. Is it so?
Yes, by defining this condition, we assume that we have some fracture opening at the tip.
Yes, some final thickness at the tip. Not elliptic fracture, not just others, but just final gap. Okay, well, many assumptions are possible, especially if you obtain some analytical solution. So it's not a sin, but I just wanted to know which are the assumptions. Okay, thank you very much.
Hello, do you hear me?
Yes.
Igor,
it's Igor Dontsov. Sorry, I cannot find a button to raise my hand, so just decided to speak up. So first of all, the comment regarding this discussion that we had, a minute ago, that these P3D and PKN models, the classical ones, they use local elasticity, right? It's one of the assumptions, and as a result, they essentially break down near the tip, right? And so therefore, the tip asymptotics and the pressure behavior near the tip is very different from the classical models, which predict singular pressure. Okay, and so if you change the elasticity to non-local, even within P3D or PKN model, then the pressure will be singular. Okay, so again, so you can think about that. Yes, in this model, the width doesn't go to 0 and pressure becomes constant. But again, it is there in the model to give roughly the correct length and height, but this near tip behavior is sacrificed. Okay, so I think this is, this is okay. But then I have the question, to Grigory more about the practical aspect of this, right? Because again, you made the fracture velocity constant, but then your injection rate is variable. which is fine, mathematically speaking. But what am I missing in terms of what is the value of this from practical perspective? Because the rate, as far as I know, is more or less constant, right? So what's the practical application of this?
Yes, I understand. I also have another self-similar solution in different assumptions, and the main idea of my study is to get several self-similar solutions which will allow me to construct more complex solution. So it is only one part of my work.
Okay, thank you.
Yeah, Grigory, and probably the final question, have you tried to compare your model with something like numerical solution of pseudo 3D or with planar 3D or with something? It would be, I think, really interesting, because if you assume constant velocity, you can get the pumping rate which is required for to have this pumping velocity, or to have this fracture velocity, and then you can compare actually.
No, I didn't.
I think it would be interesting to see, because analytical solution is always very, very good. Even if it doesn't have a practical application, you can at least use it as a kind of test, benchmark, or something like that.
It would be interesting to put this curve of fracture injection to some numerical model, more complex, and compare the results.
Yeah, it would be very interesting, I think. Okay, so thank you very much, Grigory, for interesting presentations.